Imagine a clock so precise it could run for billions of years without losing a single second. Now picture this clock as a dead star, spinning hundreds of times per second, beaming signals across the cosmos like a celestial lighthouse. This is a pulsar, and today we'll discover why these extraordinary objects are fundamental to our understanding of the universe. When we look up at the night sky, we see countless stars twinkling above us, but hidden among them are these remarkable cosmic timekeepers. Pulsars represent one of the most fascinating phenomena in our universe. They're the remnants of once massive stars that have ended their lives in spectacular supernova explosions, leaving behind rapidly rotating neutron stars that emit precise, rhythmic pulses of electromagnetic radiation. The discovery of pulsars in 1967 is a testament to how the unexpected can lead to groundbreaking scientific discoveries. When astronomers first detected these regular, perfectly timed signals from space, they were so precise and consistent that scientists seriously considered the possibility that they had stumbled upon evidence of extraterrestrial civilizations. The signals were even whimsically labeled LGM-1, standing for Little Green Men, before their true nature was understood. This initial mystery and subsequent revelation marked the beginning of a new era in our understanding of stellar evolution and the physics of extreme matter. Today, pulsars have become invaluable tools in our scientific arsenal. These cosmic lighthouses serve as natural laboratories for testing fundamental theories of physics, including Einstein's theory of general relativity. Their incredible precision and stability make them perfect cosmic tools for detecting gravitational waves, studying the interstellar medium, and even developing new methods for deep space navigation. Scientists have effectively turned these stellar remnants into a galactic GPS system, potentially paving the way for future space exploration. The story of pulsars is more than just a tale of astronomical discovery. It's a testament to the incredible phenomena that exist in our universe and how understanding them pushes the boundaries of human knowledge. As we explore the nature of these remarkable objects, we'll uncover not just their physical properties, but also their profound implications for our understanding of space, time, and the fundamental forces that govern our universe. Welcome to Exploring the Universe, your gateway to the fascinating world of astronomy. Before we dive deeper into the mysteries of pulsars, don't forget to like this video and subscribe to our channel to ensure you never miss any of our exciting content about the wonders of space. Together, we'll embark on an extraordinary journey through one of the most intriguing phenomena in our cosmic neighborhood. The birth of a pulsar is one of the most dramatic events in our universe, emerging from the spectacular death of massive stars. To understand this process, let's follow the journey of a star many times more massive than our Sun as it approaches its final moments. When a massive star exhausts its nuclear fuel after millions of years of burning hydrogen and heavier elements, it faces an inevitable collapse. This is the beginning of stellar death, a process far more violent than anything we can imagine on Earth. The star's core, no longer able to maintain the delicate balance between gravity and nuclear fusion, begins to collapse under its own enormous weight. This collapse triggers one of the most energetic events known to science, a supernova explosion. In mere seconds, the star's outer layers are blown away with unimaginable force, briefly outshining entire galaxies. The explosion is so powerful that it forges and scatters heavy elements across space, enriching the cosmos with the building blocks of future stars and planets. But it's what happens at the center of this cosmic catastrophe that truly defies imagination. The star's core, containing more mass than our Sun, is crushed by gravity into a sphere only about 20 kilometers in diameter. This compression is so extreme that electrons and protons are forced together, forming neutrons, creating what we call a neutron star. The density of this object is almost beyond comprehension. A teaspoon of neutron star material would weigh as much as all the buildings in New York City combined. Here's where one of the most beautiful principles in physics comes into play: the conservation of angular momentum. Just as a figure skater spins faster when pulling their arms close to their body, the neutron star dramatically increases its rotation speed as it contracts. This principle, which we can observe in our everyday world, scales up to create something extraordinary in space. The original star, which might have taken days or weeks to complete one rotation, is compressed into a neutron star that spins hundreds of times per second. During this transformation, something else crucial happens. The star's magnetic field becomes incredibly concentrated. As the star collapses, the magnetic field lines are squeezed together, creating a magnetic field trillions of times stronger than Earth's. This powerful magnetic field, combined with the rapid rotation, turns the neutron star into a cosmic lighthouse, a pulsar. The newly formed pulsar now rotates with almost perfect precision, sweeping beams of electromagnetic radiation across space like a celestial beacon. These beams, produced by charged particles accelerated along the magnetic field lines, can only be seen when they point toward Earth, creating the characteristic pulsing effect that gives pulsars their name. Understanding this birth process is crucial because it explains the unique properties that make pulsars such valuable scientific tools. Their incredibly stable rotation, extreme density, and powerful magnetic fields create natural laboratories for testing fundamental physics in conditions we could never replicate on Earth. From their violent births in supernova explosions, pulsars emerge as some of the most precise and useful objects in our universe, keeping perfect time across the cosmos and helping us understand the nature of space, time, and matter itself. Let's delve into the remarkable anatomy of a pulsar, exploring its structure and the mind-bending physics that make it one of the most extraordinary objects in our universe. At its core, a pulsar is a neutron star with an anatomy that defies our everyday understanding of matter. Picture an object with more mass than our sun compressed into a sphere roughly the size of Manhattan. The structure of a pulsar can be divided into several distinct regions, each with its own fascinating properties. The surface of a pulsar, called the crust, is composed of an incredibly dense lattice of iron nuclei, resembling a metallic crystal harder than anything found on Earth. This crust, though only about a kilometer thick, is so dense that a single sugar cube-sized portion would weigh as much as all human-made structures combined. Beneath this lies a mysterious realm where atomic nuclei dissolve into a sea of neutrons, creating what physicists call neutron degenerate matter. The density of a pulsar provides one of the most striking analogies in astronomy. If we were to compress Earth to match a pulsar's density, our entire planet would shrink to the size of a golf ball, yet would still maintain its original mass of nearly 6 sextillion tons. This incredible compression leads to surface gravity about 100 billion times stronger than Earth's. A marshmallow dropped on a pulsar would hit the surface with the force of 1,000 nuclear bombs. The magnetic field of a pulsar is another testament to its extreme nature. Typical pulsars have magnetic fields 1 trillion times stronger than Earth's, and in special cases, called magnetars, they can be another 1,000 times more powerful. These fields are so intense they can distort the atomic structure of matter and create vacuum birefringence, literally twisting the fabric of space itself. Near the pulsar's surface, the magnetic field is strong enough to tear atoms apart and create exotic states of matter we can barely comprehend. One of the most distinctive features of pulsars is their radiation beams. As the pulsar rotates, it emits 2 beams of electromagnetic radiation from its magnetic poles, much like a cosmic lighthouse. These beams are created by charged particles accelerated along the magnetic field lines to nearly the speed of light. The particles are forced to follow curved paths along the magnetic field lines, causing them to emit radiation across the electromagnetic spectrum, from radio waves to visible light, X-rays, and even gamma rays. The numbers associated with pulsars are equally impressive. The fastest spinning pulsars, called millisecond pulsars, can rotate hundreds of times per second, their surface moving at speeds approaching 20% of the speed of light. Despite this incredible rotation rate, they maintain stability with a precision that rivals our best atomic clocks. The Pulsar PSR J1748-2446AD holds the current record, spinning at an astonishing 716 times per second. The temperature of a young pulsar's surface can reach several million degrees Celsius, though they cool over time. Despite this intense heat, the surface appears relatively dark due to the immense gravitational field, which bends light back toward the pulsar. If you could somehow survive on the surface of a pulsar, you'd experience time dilation effects predicted by Einstein's theory of relativity. Time would pass noticeably slower than on Earth. Perhaps most remarkably, these cosmic objects maintain their structure despite their extreme conditions. The balance between gravitational collapse and quantum mechanical effects, known as neutron degeneracy pressure, keeps the pulsar stable, preventing it from collapsing into a black hole. This delicate equilibrium creates a natural laboratory for testing fundamental physics theories and our understanding of matter under extreme conditions. Understanding the anatomy of a pulsar isn't just an exercise in astronomical extremes. It provides crucial insights into fundamental physics, the behavior of matter under intense conditions, and the life cycles of stars. These cosmic lighthouses continue to surprise astronomers and push the boundaries of our scientific understanding, making them some of the most valuable objects for study in our universe. The cosmic clockwork of a pulsar is a marvel of natural precision that even surpasses human-made atomic clocks in some cases. The secret behind this incredible timekeeping lies in the pulsar's rotation, which is governed by fundamental laws of physics that ensure remarkable stability. Let's understand how this celestial timepiece works. At its most basic level, a pulsar's timekeeping mechanism is driven by conservation of angular momentum and the star's enormous mass. Once set in motion during the supernova explosion, a pulsar's rotation remains incredibly stable due to its immense moment of inertia. Think of it as a cosmic flywheel, but one that contains more mass than our Sun and spins hundreds of times per second. The precision of these rotations is astounding. The most stable millisecond pulsars lose less than a nanosecond in timing over the course of a year. To put this in perspective, if a pulsar had started spinning when the dinosaurs went extinct 66 million years ago, it would have lost less than a second in timing accuracy up to today. This level of precision makes some pulsars more stable timekeepers than our best atomic clocks. The mathematics behind pulsar timing reveals this remarkable precision. The period of rotation, p, of a typical millisecond pulsar might be around 0.001 seconds, with a period derivative, the rate of slowdown, or p, of approximately 10 to 20 seconds per second. This means that after a year, roughly 5 million seconds, the period would have changed by only delta p equals p dot times 31.5 million seconds equals 10 to the power of minus 20 times 31.5 times 10 to the power of 6 equals 3.15 times 10 to the power of minus 13 seconds. This incredibly small change in rotation period demonstrates why pulsars are such reliable cosmic clocks. For comparison, the best atomic clocks on Earth have an accuracy of about 1 second in 30 billion years, while some pulsars can achieve accuracy of 1 second in 100 million years or better. What makes this precision even more remarkable is that it's maintained despite the harsh conditions in space. The pulsar's massive gravitational field, intense magnetic field, and the surrounding space environment all work together in a complex dance that, somewhat paradoxically, helps maintain this stability. Any slight perturbation in the pulsar's rotation would be noticeable in its timing, making pulsars excellent detectors of gravitational waves and other cosmic phenomena. Scientists use a sophisticated timing technique called pulsar timing arrays, PTAs, to measure these rotations. By monitoring multiple pulsars simultaneously, astronomers can create a galaxy-sized gravitational wave detector and test Einstein's theory of general relativity. The precise arrival times of pulsar signals are measured using atomic clocks on Earth, and any variations from the expected arrival times can indicate the passage of gravitational waves or other cosmic events. Speaking of timing measurements, here's a simplified equation that astronomers use to predict pulse arrival times. T arrival, true T0 plus NP plus 1 2PN2 plus timing corrections, where T0 is the reference epoch, N is the number of pulses since T0, P is the pulse period, P is the period derivative. Timing corrections account for various effects like Earth's motion and relativistic effects. If you're as amazed as we are by these incredible cosmic timepieces, don't forget to hit that like button and share your thoughts in the comments below. What do you think would be the most precise time in the universe? Could it be the steady beat of a millisecond pulsar, or perhaps the synchronized ticking of multiple pulsars across our galaxy? Your imagination is the only limit when we explore these fascinating cosmic phenomena. Remember, every pulsar out there is not just a collapsed star. It's a testament to the precise and orderly nature of our universe, keeping time across the cosmos with an accuracy that continues to astound scientists and astronomers alike. Let's explore the fascinating diversity of pulsars, each type offering unique insights into the physics of extreme matter and energy in our universe. Radio pulsars are the classic lighthouse of the cosmos, and they're what astronomers first discovered back in 1967. These pulsars primarily emit radio waves and represent the most common type we observe. Their radio emissions come from charged particles accelerated along magnetic field lines near the pulsar's magnetic poles. What makes them particularly useful is that radio waves can penetrate through much of the interstellar medium, allowing us to detect them from great distances. Most radio pulsars rotate about once per second, though their periods can range from about 0.1 to 10 seconds. X-ray pulsars represent a more energetic class of these cosmic objects. They're typically found in binary systems where the pulsar is actively pulling matter from a companion star. As this material falls toward the pulsar, it becomes superheated to millions of degrees, emitting intense X-ray radiation. The process creates what astronomers call an accretion disk around the pulsar, and as the star rotates, we observe regular pulses of X-ray emission. These systems provide valuable laboratories for studying how matter behaves under extreme gravitational and magnetic conditions. Millisecond pulsars are the speed demons of the pulsar world, rotating hundreds of times per second, so fast that their surfaces move at significant fractions of the speed of light. These remarkable objects are thought to be recycled pulsars, spun up to their incredible speeds by accreting matter from companion stars over millions of years. The fastest known millisecond pulsar, PSR J1748-2446 AD, spins at an astonishing 716 times per second. Despite these incredible rotation rates, millisecond pulsars are extraordinarily stable, making them invaluable for timing experiments and gravitational wave detection. Magnetars are perhaps the most extreme members of the pulsar family. These rare objects possess the strongest magnetic fields known in the universe, up to a quadrillion, 10 by 15 times stronger than Earth's magnetic field. Such powerful magnetic fields can actually affect the quantum structure of atoms and cause bizarre phenomena like vacuum birefringence. where the very fabric of space becomes twisted. Magnetars occasionally produce enormous bursts of energy called giant flares, releasing more energy in a fraction of a second than our sun does in many years. These bursts are so powerful they can be detected from other galaxies. Binary pulsars. These are pulsars orbiting another star or another pulsar. The most famous example is the Hulse-Taylor binary pulsar, which provided the first indirect evidence for gravitational waves and earned its discoverers the Nobel Prize. Young pulsars. These are recently formed pulsars, like the one in the Crab Nebula. They spin relatively quickly, but not as fast as millisecond pulsars, and are often surrounded by beautiful nebulae created by their powerful energy output. Intermittent pulsars. These mysterious objects switch between active and quiet states, sometimes appearing to turn off their pulsar mechanism entirely for periods ranging from minutes to years. Each type of pulsar offers unique opportunities for scientific research. Radio pulsars help us map the distribution of matter and magnetic fields in our galaxy. X-ray pulsars reveal how matter behaves in extreme gravitational fields. Millisecond pulsars serve as ultra-precise cosmic clocks for detecting gravitational waves. Magnetars provide natural laboratories for studying physics in magnetic fields stronger than we could ever create on Earth. Understanding these different types of pulsars has revolutionized our knowledge of stellar evolution, nuclear physics, and even the fundamental forces of nature. Each new discovery in pulsar astronomy brings us closer to understanding some of the most extreme conditions in the universe, while often raising new questions that challenge our existing theories of physics and astronomy. The diversity of pulsar types demonstrates how a single class of astronomical object can manifest in dramatically different ways, each offering unique windows into the physics of our universe. As our detection methods improve and our understanding deepens, we may yet discover even more varieties of these fascinating cosmic lighthouses. Let's explore the remarkable practical applications of pulsars, which extend far beyond their astronomical significance to influence space exploration, fundamental physics, and potentially future navigation systems. Space navigation. Using pulsars represents one of the most innovative practical applications of these cosmic lighthouses. NASA and other space agencies are developing X-ray pulsar-based navigation systems that could revolutionize deep space travel. This system works similar to GPS but on a galactic scale. By measuring the precise arrival times of pulses from multiple pulsars, spacecraft can determine their position in space with remarkable accuracy. The advantage of this system is that it's completely autonomous and works anywhere in the solar system, unlike traditional navigation methods that rely on ground-based communications. Pulsars have proven invaluable for testing general relativity, providing some of the most stringent tests of Einstein's theory. Binary pulsar systems, where a pulsar orbits another star or another pulsar, offer perfect laboratories for studying gravitational physics. The extreme conditions around pulsars, intense gravity, high velocities, and strong magnetic fields allow scientists to test aspects of general relativity that are impossible to verify on Earth. The Hulse-Taylor binary pulsar, for instance, demonstrated the existence of gravitational waves through the precise measurement of its orbital decay, earning the 1993 Nobel Prize in Physics. The detection of gravitational waves represents another crucial application of pulsar observations. Scientists use pulsar timing arrays, networks of precisely timed millisecond pulsars, to detect gravitational waves from supermassive black hole mergers and other cosmic events. These arrays work by monitoring slight variations in the arrival times of pulsar signals caused by gravitational waves passing through space. This technique complements other gravitational wave detectors like LIGO, but is sensitive to much lower frequencies, allowing us to detect different types of cosmic events. The pulsar positioning system is perhaps one of the most ambitious practical applications being developed. Similar to GPS but operating on a galactic scale, PPS could provide autonomous navigation throughout the solar system and beyond. Here's how it works. Multiple pulsars serve as reference points, each emitting precisely timed pulses. A spacecraft equipped with X-ray detectors receives these pulses. By comparing the arrival times of pulses from different pulsars, the spacecraft can calculate its position in three-dimensional space. The system could achieve accuracy within 5 kilometers at the distance of Neptune. Beyond these major applications, pulsars serve several other practical purposes. Timekeeping. Millisecond pulsars are so stable they could potentially be used to create a pulsar time standard that might eventually rival or complement atomic clocks. Interplanetary Internet. The regular pulses from pulsars could potentially be used to synchronize communication systems across the solar system, enabling an interplanetary communication network. Space weather monitoring. Variations in pulsar signals can help scientists monitor the interstellar medium and solar wind, contributing to space weather forecasting. Astronomical reference frame. Pulsars help establish a precise reference frame for measuring positions and motions in our galaxy, crucial for both astronomy and space navigation. Current technology development focuses on making these applications more practical. Miniaturization of X-ray detectors for spacecraft navigation, development of more sensitive pulse detection systems, creation of comprehensive pulsar timing models that account for all known effects, implementation of artificial intelligence algorithms to process pulsar data more efficiently. The future potential of pulsar applications is vast. Autonomous deep space navigation systems, more precise tests of fundamental physics, enhanced gravitational wave detection capabilities, improved understanding of space weather and its effects, development of new timing and positioning technologies. As our technology advances and our understanding of pulsars deepens, we can expect to discover even more practical applications for these remarkable cosmic objects. Their precise nature and ubiquitous presence throughout the galaxy make them invaluable tools for both scientific research and practical space technology, helping humanity push the boundaries of space exploration and our understanding of the universe. The fastest known pulsar in our universe, PSR J1748-2446 AD, is a true cosmic speedster that pushes the boundaries of physics. This remarkable object spins at an almost unimaginable rate of 716 times per second. That's faster than some kitchen blenders. To put this into perspective, a point on its equator is moving at approximately 24% the speed of light. If this pulsar spun just a little faster, it would literally tear itself apart due to centrifugal forces. Scientists believe this might be close to the theoretical speed limit for pulsar rotation, making it a fascinating subject for studying the extreme physics of matter and motion. In 1992, astronomers made a groundbreaking discovery that changed our understanding of planetary systems. The first confirmed exoplanets were found not around a regular star like our Sun, but orbiting a pulsar named PSR B1257+12. This discovery was completely unexpected. How could planets exist around such an extreme object? The system contains 3 planets whirling around the pulsar in nearly circular orbits. These planets, sometimes called pulsar planets, likely formed from the debris left over after the supernova that created the pulsar. They exist in an incredibly hostile environment, bathed in intense radiation and subject to enormous gravitational forces. This discovery opened our eyes to the possibility that planets could form in the most unlikely places in the universe. Pulsars serve as incredible natural laboratories for studying gravity. Their intense gravitational fields and precise rotational periods make them perfect tools for testing Einstein's theory of general relativity. When a pulsar is paired with another star in a binary system, scientists can observe fascinating gravitational effects that are impossible to see elsewhere. For instance, the bending of space-time around these systems is so extreme that we can measure how time itself slows down in strong gravitational fields, an effect called gravitational time dilation. These observations have provided some of the most stringent tests of general relativity and continue to help us understand the fundamental nature of gravity. One of the most puzzling phenomena associated with pulsars is what astronomers call glitches. These are sudden increases in a pulsar's rotation speed, like a cosmic hiccup. Imagine a perfectly precise cosmic clock suddenly starting to run a tiny bit faster. These glitches occur when the pulsar's rigid crust suddenly shifts, similar to earthquakes on Earth, but far more dramatic. The interior of a pulsar is thought to be a superfluid, a state of matter that flows without friction. Scientists believe that glitches happen when this superfluid interior suddenly transfers some of its rotation to the pulsar's crust. These events provide rare glimpses into the internal structure of neutron stars and help us understand the exotic states of matter that exist under extreme conditions. A particularly fascinating glitch occurred in the Vela pulsar in 2016, which astronomers were lucky enough to catch in real time. This event showed that these speed-ups can happen in less than 10 seconds, incredibly fast for such a massive object. These observations continue to challenge our understanding of nuclear physics and the behavior of matter under extreme conditions. The study of these pulsar curiosities has led to numerous unexpected discoveries. For instance, we've learned that some pulsars can switch their magnetic poles, effectively turning themselves off and on over time. Others exhibit mysterious variations in their pulse patterns that we still can't fully explain. Each new discovery adds another piece to the puzzle of these fascinating cosmic objects, reminding us that even after decades of study, pulsars continue to surprise and amaze us with their extraordinary properties and behaviors. These incredible features of pulsars not only captivate our imagination, but also push the boundaries of our scientific understanding, making them some of the most valuable objects for studying the extremes of our universe. They continue to be a source of fascinating discoveries, helping us unravel the mysteries of space, time, and matter itself. Dr. Jocelyn Bell Burnell's discovery of pulsars in 1967 revolutionized our understanding of stellar evolution. As she once eloquently described her historic discovery, the signal was pulsing with great regularity, with a period of about 1 1/3 seconds. It was an entirely artificial-looking signal, yet it came from a fixed point in the sky. In more recent reflections, she has emphasized how this discovery opened new frontiers in physics. Pulsars have given us a far richer understanding of the universe than we could have imagined. They've become precision tools for testing Einstein's theory of relativity and may even help us detect gravitational waves. Current radio astronomy research is pushing the boundaries of what we know about pulsars. Dr. Victoria Caspi, a leading pulsar researcher at McGill University, explains, "We're now able to observe pulsars with unprecedented precision. Every new observation has the potential to challenge our understanding of physics under extreme conditions." Teams worldwide are using advanced radio telescopes like the Square Kilometre Array and the 500-meter Aperture Spherical Telescope to study pulsars in unprecedented detail. Looking to the future, pulsar research holds immense promise. Dr. Scott Ransom from the National Radio Astronomy Observatory predicts, within the next decade, pulsar timing arrays may detect the gravitational wave background from supermassive black hole mergers throughout the universe. This would open an entirely new window for observing cosmic phenomena. Other experts highlight the potential technological applications. Dr. Andrea Lohmann, known for her work in pulsar timing, suggests pulsars could become the GPS system of the future, guiding spacecraft through the solar system with incredible precision. We're just beginning to tap into their potential for space navigation. Now let's engage in a thought-provoking interactive exercise. Pause the video for a moment and consider this mind-bending question. If you could somehow stand on the surface of a pulsar, how much would you weigh? The answer is truly astonishing. If you weigh 150 pounds on Earth, on a typical pulsar, you would weigh about 15 trillion pounds. That's because a pulsar's gravitational field is roughly 100 billion times stronger than Earth's. Your body would be instantly crushed by this enormous gravitational force. In fact, you'd be stretched and compressed into a layer thinner than a single atom. This extreme example helps us understand why pulsars are such extraordinary laboratories for studying the laws of physics under extreme conditions. Recent research initiatives that experts are particularly excited about include the search for pulsar black hole binary systems, which could provide unprecedented tests of general relativity using arrays of millisecond pulsars to detect low-frequency gravitational waves, studying pulsar glitches to understand the internal structure of neutron stars, developing more sophisticated pulsar-based navigation systems for deep space missions. As Dr. Duncan Lorimer, another prominent pulsar researcher, notes, each new generation of radio telescopes brings discoveries we couldn't have anticipated. Pulsars continue to surprise us and push our understanding of fundamental physics to new limits. The expert consensus is clear. Pulsars remain one of our most valuable tools for probing the mysteries of the universe. As we develop more advanced observational techniques and technologies, these cosmic lighthouses will continue to illuminate our understanding of the fundamental laws that govern our universe, while possibly enabling new technologies that could revolutionize space exploration. The story of how pulsars revolutionized our understanding of gravitational waves reads like a scientific thriller. For decades after Einstein predicted their existence, gravitational waves remained elusive, their subtle effects seemingly impossible to detect. However, pulsars, with their incredibly precise timing, emerged as unexpected heroes in this cosmic quest. When gravitational waves pass through space, they create ripples in the fabric of space-time. These ripples subtly affect the timing of pulsar signals reaching Earth. By monitoring an array of millisecond pulsars across the galaxy, astronomers created a vast cosmic detector, turning our entire galaxy into an observatory. This technique, known as pulsar timing arrays, can detect gravitational waves that are far too low in frequency for ground-based detectors like LIGO to observe. In 2023, scientists announced a major breakthrough. Multiple PTA collaborations detected evidence of a gravitational wave background, a cosmic orchestra of gravitational waves produced by supermassive black holes merging across the universe. This discovery opened an entirely new window into the cosmos, allowing us to observe phenomena that are invisible to traditional telescopes. The connection between pulsars and space-time goes even deeper. These cosmic lighthouses serve as natural laboratories for testing Einstein's theory of general relativity. Their intense gravitational fields bend space-time so severely that time itself flows differently near their surfaces. When pulsars orbit other massive objects, they create perfect environments for studying how gravity warps the fabric of space and time. Perhaps the most profound revelation is how pulsars demonstrate the deep connection between gravity and time. The precise timing of pulsar signals has shown us that gravity isn't just a force. It's a distortion in the fabric of space-time itself. When we observe delays or variations in pulsar signals, we're not just seeing the effects of gravity. We're witnessing the dynamic, flexible nature of space-time responding to the dance of massive objects across the cosmos. The future holds even more promise. As our detection methods improve and more sensitive instruments come online, pulsars will help us map the gravitational wave sky, potentially revealing hidden supermassive black hole mergers, cosmic strings, and perhaps even echoes from the early universe itself. Each new discovery brings us closer to understanding the fundamental nature of space, time, and gravity, the very framework of our universe. This convergence of pulsars, gravitational waves, and space-time has transformed our understanding of the cosmos. What began as mysterious regular pulses from distant stars has evolved into one of our most powerful tools for probing the deepest mysteries of the universe, revealing a reality far more fascinating and interconnected than we ever imagined. The influence of pulsar research on GPS technology represents one of the most practical applications of these celestial objects in our daily lives. While our current GPS systems don't directly use pulsars, the precise timing techniques developed for pulsar observations have revolutionized how we approach satellite navigation. The extremely accurate atomic clocks used in GPS satellites borrowed many principles from pulsar timing methods. These innovations have made modern navigation so precise that your smartphone can pinpoint your location within a few meters anywhere on Earth. Looking beyond our planet, pulsars are poised to transform space navigation in ways that seem almost like science fiction. NASA and other space agencies are developing X-ray pulsar-based navigation systems, or XNAV, which could become the interplanetary equivalent of GPS. Unlike traditional navigation methods that rely on communication with Earth, XNAV would allow spacecraft to determine their position anywhere in the solar system autonomously. Imagine future missions to Mars or beyond, using pulsars as cosmic lighthouses, guiding ships through the vast ocean of space with unprecedented accuracy. The implications for deep space exploration are profound. As we venture further into the solar system, traditional navigation methods become increasingly impractical due to the time delays in communications with Earth. A pulsar-based navigation system could provide real-time positioning data to spacecraft billions of miles from home. This technology could prove crucial for missions to the outer solar system, automated cargo ships supplying future Mars colonies, or even the first human missions beyond our solar system. Our growing understanding of pulsars has also transformed how we view our place in the cosmos. These objects have become natural laboratories for testing fundamental physics theories, including Einstein's theory of relativity. Their study has revealed the extreme conditions possible in our universe, showing us how matter behaves under pressures and densities impossible to recreate on Earth. This knowledge has practical applications in fields ranging from nuclear physics to materials science. The human context extends beyond technology to our philosophical understanding of the universe. Pulsars have shown us that the cosmos operates with an underlying precision we never imagined possible. These cosmic lighthouses, spinning with almost perfect regularity, challenge our perception of time and space. They remind us that in an apparently chaotic universe, there exist objects of remarkable order and stability. Looking to the future, pulsar research promises even more exciting developments. Scientists envision a galactic positioning system using pulsars, enabling precise navigation throughout our entire galaxy. This could be crucial for humanity's long-term ambitions of becoming a spacefaring civilization. The technology could also help us create more accurate maps of our galaxy, better understand dark matter distribution, and potentially detect gravitational waves from the early universe. For the average person, these developments might seem distant from everyday life, but their impact is more immediate than we might think. The same technology that helps us study pulsars has led to improvements in medical imaging, telecommunications, and our understanding of fundamental particles. Every time you use your smartphone's GPS to navigate to a new restaurant or track your morning run, you're benefiting from techniques originally developed to study these fascinating cosmic objects. The study of pulsars also reminds us of humanity's capacity for discovery and innovation. From their accidental discovery in 1967 to their potential future role in interstellar navigation, pulsars represent the remarkable journey of human knowledge from pure scientific curiosity to practical application. They show us how basic research, driven by nothing more than the desire to understand the universe, can lead to technological breakthroughs that benefit all of humanity. As we continue to push the boundaries of space exploration and technological innovation, pulsars stand as beacons lighting the way forward, not just for navigation, but for our understanding of the fundamental nature of the universe itself. They remind us that in studying the cosmos, we're not just looking outward at distant objects, but developing tools and knowledge that will help shape humanity's future among the stars. As we conclude our journey through the fascinating world of pulsars, we've discovered that these remarkable objects are far more than just cosmic timepieces. They represent nature's most extraordinary laboratories, offering us windows into the fundamental laws of physics and the deepest mysteries of our universe. Throughout our exploration, we've seen how pulsars challenge our understanding of matter, energy, and the very fabric of space-time. From their violent births in supernova explosions to their role in detecting gravitational waves, pulsars continue to reveal new insights into the cosmos. Their incredibly precise rotations, extreme densities, and powerful magnetic fields create conditions we could never replicate on Earth, allowing us to test theories of physics at the very edge of our understanding. The practical applications of pulsar research extend far beyond pure science. These cosmic lighthouses are helping us develop new navigation systems for space exploration, improve our timekeeping technology, and may one day guide humanity's journey to the stars. Each new discovery about pulsars brings us closer to understanding not just these extraordinary objects, but the fundamental nature of the universe itself. Perhaps most importantly, pulsars remind us of the incredible precision and order that exists in our seemingly chaotic cosmos. They stand as testament to the power of human curiosity and ingenuity, showing us how careful observation and scientific thinking can unlock the deepest secrets of the universe. From their accidental discovery to their current role in cutting-edge physics, pulsars continue to inspire new generations of scientists and demonstrate that there is still so much to learn about our cosmic neighborhood. As we look to the future, pulsars will undoubtedly continue to surprise us, challenge our theories, and push the boundaries of our knowledge. They remain silent sentinels in space, keeping perfect time across the cosmos while helping us unravel the greatest mysteries of modern physics. In studying pulsars, we're not just observing distant stars, we're touching the very foundations of reality itself. Before we end this cosmic journey, remember to subscribe to Exploring the Universe to stay updated with more fascinating content about the wonders of space. Turn on notifications by clicking the bell icon so you never miss our latest uploads. If you enjoyed this exploration of pulsars, please give this video a thumbs up and share it with your friends who might also be interested in the mysteries of the cosmos. Together, let's continue our adventure through the most extraordinary phenomena our universe has to offer.